Hey everyone, so in this video we want to talk about stiffness and specifically stretch stiffness and bend stiffness in our cloth constraint here. So if you run this is how our test scene looks like, very simple. And it's important to understand what the two actually mean because it's not as intuitive as it seems. So let's start with the bend stiffness. The bend stiffness is relatively low, it's set to 1 here, but the multiplier is 0.001. And this means it's pretty low. And then we have the stretch stiffness, which is really high. It says 1 here, but then it's multiplied with a 1 with 10 zeros. So very high number, very low number. And actually the bend, even though it's very, very low, is actually still a bit too high in my opinion for the defaults. Anyway, so what the bend stiffness does first, because it's a more important one in my opinion for cloth, is this. And we can see that here in this example quite well for something like this, right here. This is actually something that we want to prevent, and we will look at ways to not have this stepping, but this is actually a great example of explaining what bend does. The bend stiffness stops the edges to get a certain angle around the points, or don't angle too much around the points. So this is what limits that, and it defines how much, the edges can bend around points. In practical terms, what that means in the end is folds, and how many folds you get and how fine those folds are. So if you look at this, we have a couple of folds, obviously. So this is the default. And let me decrease this to 0.1, so by 1/10. And what you should see is, and I think we can see this quite well, is we get more folds or finer folds. Maybe the best way of comparing this is putting it next to each other, two versions, and then have a look at the different results. And for fun, let me increase that to maybe 30 this time. So on the left, we have a bend stiffness of 30, and on the right, a bend stiffness of 0.1. And you can see what I mean. We have more folds and we have finer folds. And this is usually what you want with cloth. So this is pretty straightforward. And you can just imagine how a piece of material would behave when you let it fall over your hand, for example. So this is usually how I think about it. And an example would be a normal piece of cloth, a piece of rubber, and a piece of paper, for example. So different materials obviously create different amount and levels of folds. So this is bending, and you can directly see the result. And the next one is stretching. Let's delete all this and go back to our example here. And let's decrease our stretch stiffness to something like 0.001. Let's actually go even further down. And basically what you get here is something that is, basically rubber, very thin rubber. Let's go even further. I mean, one way of doing this is adding zeros to this, or we could of course just say, okay, 1, and then we go to multiply with 100. That might be a more reasonable approach. And if we go to something really low, like 0.1, you get this. So something that is really stretchy, to the point that it's really unrealistic. And this is important to remember. Cloth actually doesn't behave like that. So be careful with your stretch stiffness. And the best way to think about this is if you take a material and you try to pull it apart, how much can you stretch it actually? And as you know, a piece of rubber, for example, you can bend quite a lot, but cloth, and that is interesting, actually you can't. So if you take cotton, for example, you can't actually pull it apart that much. So maybe, surprisingly, the stretch stiffness of cloth is actually pretty high. And this is why the default is the way it is, with 10 zeros after the 1. And usually what I do is I always lower the bend stiffness in my kind of standard workflows. That's just something I noticed. I usually lower the bend and keep the stretch stiffness unless I have something really exotic as a material. It becomes interesting when we think about something more stiff than normal cloth. For example, paper. So if you imagine paper falling on your hand, it does not bend around your hand, but it's actually staying relatively intact. So let's actually try that, and then we see a pretty common problem with vellum. So the idea would be here that we increase the bend stiffness to something pretty high. Let's try 1000 and see what happens. And you get this. Okay, this is still way too bendy and soft for paper. So let's go higher. Let's do 1,000,000. It didn't change much, did it? So how high can we go? Let's try, 10 zeros. And you know what? It's on top, add a couple of zeros in the multiplier. So really some insane number now. And what we still get is this. So what's going on? This is a common problem with vellum and very stiff materials. And that is that you actually have a hard time to get something very stiff. There are two solutions I would recommend. There are probably more, I don't know. But the first one, the classical one, is simply to increase your calculation iterations, which means in your Vellum solver, there is actually currently a substep of 1 and 100 times a calculation per frame that calculates the positioning of the points relative to each other, controlled by the constraints. That's the best way of thinking about it. By increasing that number, basically you make the whole thing stiffer because the calculation of the constraints happens more often. So if you will, it means I calculate the stiffness more often, and by doing this, it becomes more stiff. That's kind of the logic. So instead of changing the substeps, you can just increase the constraint iterations. Let's try 300 instead of 100 and see what happens. And of course, what happens at first is it becomes slower. And maybe you can see that it actually became a bit stiffer. So let's go a bit higher even and try 1,000. And now you can really feel that it goes slower, but I think we start to see that it also becomes quite stiff. So let's go even further. Again, our goal here is paper. Let's try 5,000, which at this point really becomes a bit nuts because you can see how slow this whole thing gets. But you can see actually it's surprisingly close to paper now. Not perfect, but it helped. So as you can see, increasing the constraint iterations actually helps. Now, because again, the stiffness is calculated more often and that results in more stiffness. So an alternative to that could be actually, and this is what I would recommend, is instead of increasing the constraint iterations, in my experience, what also helps is, I mean, you can raise it a little bit, let's say to 300 to increase the substeps. What happens here, of course, is you have 5 times multiplied with 300 constraint iterations, and for some reason it is a good idea to mix it into the substeps. So just keep that in mind, even though I can't fully explain that to you why that is. And as you can see, we have actually lower constraints overall, the speed is higher, but we have a similar result. So instead of 5,000 iterations, we should technically now have 1,500, yet we have the same stiffness as with 5,000. And here you can see why I would recommend doing it this way, even though it doesn't really logically make too much sense, to me at least. So I think one reason could be that the smoothing iterations are also run more often, so it's averaged out more often. That could be. Anyway, so this is one solution, but the problem, of course, is it becomes pretty slow, and I think that's not always necessary. The second approach is a bit more interesting. Let's put all this back to the defaults. And what you can do is you can instead just lower the resolution of your input geometry. So let's copy our grid here and let's lower the amounts to something like 10 by 10 or 20 by 20. Let's not be too aggressive. Something like this. And again, remember, we set the constraint iterations back, and let's run this now and see what happens. And as you can see, it's much stiffer. If I lower the subdivision even further, you will see that the result gets even more extreme. It gets harder and harder. So as you can see, the amount of points we have in a geometry does influence the calculation of the stiffness. And the explanation for that goes something like this. So if you have 4 points, let's say, that build your cloth object, then what your bend stiffness basically says, and it actually isn't exactly that, but it's a good way of imagining it, is how far in degrees can your point rotate around the next point. So if we say we limit it to 5 degrees, then this would look like this. Each point can rotate 5 degrees roughly relative to the other one. So the maximum bending you could achieve here is something like this. Now imagine this with something with way more points, and we apply the same rule, every point can rotate by 5 degrees, then it would look something like, let's see if I can do this, something like this. And we had 4 and 4, yeah, so one more, something like this. Let's assume they all rotate only 5 degrees around each other. Then you still get, just because of the amount of points, a much stronger bend, because the degrees, of course, accumulate. So that's kind of the logic. So as you can see, it's very stiff, yet you don't sacrifice speed. So it's a pretty good way of, at the very least, speeding up the idea. You can still combine the two, of course, by increasing the steps or the iterations, or both, and lowering the resolution just a little bit, and then you get a kind of the best of both worlds. But the question, of course, that arises is, okay, Christian, that works fine with a grid, but if I have something complex, how do I do this when I still want to render my high-res version, right? And that's totally a reasonable question. Now, what you can do, and that's a general approach in a lot of simulations, you actually render your high-res version. So let's say we have something that is a bit more complex, and for some weird reason, this is what you or your client want as your piece of cloth, some kind of, I don't know, tapestry or whatever. And what you do is you take another object that has a lower resolution but the same shape, and you simulate with that, and then you apply the result of the simulation to your high-res version. How do you do that? Well, actually, we've already seen a node that does that, and that is the pointiform, because we can just use we want to deform the high-res version. We have a reference, which is our low-res version that we use only for our simulation. And then we have the result of our simulation, which looks like this, that we can then use to deform the original one. And you can see that works quite well. And the behavior is just applied from the low-res version to the high-res version. So that works quite well. The reason I use a pointiform here is that I want to show you that this is actually something we already know and we already know how to use. And this is one of the examples where you can use the pointiform. And if you can't fully remember how that works, please watch the video again about the pointiform. You can search it in the search bar. And also what's important here, if you have some kind of problems, remember that you can change the amount of minimum points to kind of average out the deformation, and then very often some irregularities can be calculated away. Now the thing is, the pointiform, since we already know that, is an absolutely legitimate approach for this. There's also actually a built-in very similar approach purely for Vellum, and that is called cloth deform. And as you can see, it has 3 inputs. And at first glance, it seems like it works the same way because it has the exact same inputs as the pointiform. So let's quickly put in all the stuff, and it complains. It can't work just like that because it needs to work in combination with another node called cloth capture. And the way this works is you put it into the deforming input, and then the second input of that node is the rest geometry again. And the idea here is, and there's the difference between that approach and the pointiform, that you have a bit more kind of visual control over the influence range. So the influence range in the pointiform is 0.1, which you have to increase or decrease depending on your case. And the same is true for cloth capture, with the difference that you can see it. And if you want, you can also visualize it in form of color. So here you can see directly how much influence each point has. And this then works pretty much the exact same way as a pointiform, which you can see here. And to my knowledge, there is absolutely no difference between the two, other than visualizing the weights, basically. And the main idea here is that you have, with cloth, a bit more control over this. But the pointiform is essentially the exact same thing, which you can also see by just playing around with the numbers. You will see that the result is the same if you set it to the same, for example, radius. So to my knowledge, there is no obvious advantage for cloth over pointiform, cloth capture and cloth deform over pointiform. But I just wanted to make you aware that there is basically a more advanced version of it. But I so far only used the pointiform without any problems whatsoever. Okay, so this is how you work with stiffness. Pretty important. We talked about a couple of things, how to make very strong stiffness, then what is bend and stretch stiffness in the first place. And then finally, when we use the trick of using low res version instead of the high res version to simulate very stiff objects, we can use a point deform or the cloth deform to then use the high res version for rendering. Okay, so I hope this is helpful. Thank you very much and see you later. Cheers.